And this one? Oh, this one's working.
Testing. Okay, wonderful. Thank you. Morgan. So this is machine learning, and this is Katharine Beaumont. We'll introduce ourselves a little bit. I'm James Weaver, work for Pivotal. Katharine's with Voxed. We both have this incredible interest in machine learning and have been coming up with some curriculum and teaching it at various places. And we'd just like to know, how many of you have some experience with machine learning? Some experience, okay? How about a lot of experience? A lot of experience. So, a lot of experience? No. Oh, who has a lot of experience with machine learning?
I definitely saw a hand at the back.
Okay.
Maybe.
Because I'm wondering, okay, good. So if there are questions we can't answer, we'll ask you. Okay, so that's who we are. I'll let Katharine explain a little bit more about who she is.
So I work for Voxed, so you might have recognized that the title of the conference is Voxed Days, if you're observant. And Voxed sits behind Voxed Days, and we write content that connects the different conferences together. You might see me on YouTube interviewing speakers, and we promote the content from the conferences. So I go to different conferences, interview people, sometimes get roped into panels or speaking, and try and do some development when I have time, which is a tiny amount of time.
And Katharine's being modest. She's got a deep background in mathematics, which is when we get into the parts of the math for machine learning that I don't fully understand, I'm going to punt to Katharine, and then she'll take it the rest of the way and really give us intuition and maths on those areas. My name is James Weaver. I work for Pivotal. I've been a Java developer forever. I've written several books. And am a Java champion, Java rockstar speaker. I play well with others. I got that award in kindergarten, so I've got that going for me. And what we'd like to do now is we've both taken this course by Andrew Ng, or Ng or whatever, and he's a luminary in machine learning. He was one of the co-founders of Coursera, and he is a professor at Stanford, and he's the chief scientist at Baidu. And this is the introductory video from that course. And so I'd just like to kick things off by playing that video.
What is machine learning? You probably use it dozens of times a day without even knowing it. Each time you do a web search on Google or Bing, that works so well because their machine learning software has figured out how to rank web pages. When Facebook or Apple's photo application recognizes your friends and your pictures, that's also machine learning. Each time you read your email and a spam filter saves you from having to wade through tons of spam, again, that's because your computer has learned to distinguish spam from non-spam email. So that's machine learning. It's a science of getting computers to learn without being explicitly programmed. One of the research projects that I'm working on is getting robots to tidy up the house. How do you go about doing that? Well, what you can do is have the robot watch you demonstrate the task and learn from that. The robot can then watch what objects you pick up and where to put them and try to do the same thing even when you aren't there. For me, one of the reasons I'm excited about this is the AI, or artificial intelligence problem. Building truly intelligent machines which can do just about anything that you or I can do. Many scientists think the best way to make progress on this is through learning algorithms called neural networks, which mimic how the human brain works. And I'll teach you about that too. In this class, you learn about machine learning and get to implement them yourself. I hope you sign up on our website and join us doing that. Well,
one of the key research projects that I'm working was the definition, that the way that he defines machine learning. Machine learning is the science of getting computers to learn without being explicitly programmed. So as developers, we're used to writing all of the procedural or object-oriented or functional code that makes a computer do something. And so we're kind of teaching the computer how to do something through code. Machine learning is the science of getting it to learn without explicitly programming it that way. And so what we're going to explore then is the technologies involved in pulling that one off. So where have we seen machine learning in the real world? Well, we're seeing, of course, self-driving cars. We're able now to generate image descriptions. So if it's presented in an image, it can tell you not only what's in the image and what's happening in the image, but then also in a language, English, German, whatever, be able to describe what's happening in the image. And so that's through machine learning. Now there are 3 types of machine learning. It's broadly categorized into 3 types. The first one is supervised, the next one is unsupervised, and the next one is reinforcement learning. So in a nutshell, supervised learning is the idea where you have you're training a model where you have inputs, also known as features, and then you train it with the correct answers. For example, from the NG course, the Coursera course, there's a very simple model where as input, one of the only feature is a house size in square meters. And then we have housing prices in the thousands of euros. And so then how do we map those? How do we teach, through machine learning, how do we make it so that the machine can learn to predict, given a square meter of a house, how many euros it should cost? So we do that by teaching it using real data. We supply the answers, and so we give it size in square feet. And so those are those data points, size in square feet on the x-axis, and the y-axis, the price. And you notice where the data points exist. And then the machine learning task then is, okay, I'm going to give you 250 square meters. You tell me, the computer, you tell me, you predict how much that should cost. So then there's unsupervised learning. So unsupervised learning, you don't give it the correct answers. You give it data, and then it finds the structure in the data. One of the most popular algorithms and reasons for unsupervised learning is the ability to find clusters. Where is the data clustered? And then, for example, here's an example of clustering. It's on the Google Brain site, Google Arts and Culture Experiment, where it takes works of art, thousands of works of art pieces from all over the world, and clusters them according to visual characteristics. So this is just a visualization of that. For example, if I wanted to go find ballet dancers, so I could go here. Now these aren't tagged ballet dancers or anything like that. It's just there are images that are more similar to each other than others. And so the clustering algorithms, the algorithms used, the unsupervised algorithms, are then clustered those ballet dancers together, apart from, for example, some other works of arts that had less visual characteristics, similarities. And then the last one is reinforcement learning. So the idea there is you have this agent that could be representative of something in the real world, and you're trying to teach it to do something. And the way that you teach it is you give it rewards. And so it could be points or whatever. And then as it successfully completes a task, then you reward it. And so it then learns to optimize toward completing that task correctly. So AlphaGo, the Google DeepMind project, where the application, this machine learning application, beat the world master in Go, is an example of using reinforcement learning along with other unsupervised and supervised techniques. So now we're going to dive into supervised learning, and Katharine is going to take it from there and kind of dive in here.
This is Maths Dog. Just to warn you that some maths is coming up and you don't need to be scared. But not too much and not too complicated. So linear regression is the first example we saw with the house prices. So the size of the house versus the price. So I took some examples from where I used to live, where the houses, you might see the houses were more affordable. We've got 10 examples, and if we plot them on a graph, it looks like this. So what we want to do with linear regression is try and find out if there's a linear relationship between this value down here, size in square feet, and price in thousands. So just to remind you the equation of a straight line, I'm sure you're familiar with it, but just in case anyone isn't, we've got y equals mx plus c. So m is the gradient, and that's the rate of change. So that's how steep the line is. And c there is where we're going to intersect the y-axis. So we're going to change that very slightly for our example here. And just by convention, we use theta, or however you want to pronounce it. And that's just a symbol. So instead of using m and c, we're going to use theta 0 and theta 1 just to indicate the first element and then the second element. Because as we get more and more complicated examples, we might have hundreds of thetas and run out of m's and c's.
Who is scared of theta, by the way? Okay, so can you make us less afraid of theta?
It's just a 0 with the line in it.
Okay, but it's exactly the same. You're using it for exactly the same purpose as as what up there?
So if you move the c down from there to there, c is going to be theta 0, so that's going to be our intercept. And later on when we use that again and again, we start referring to it as a bias term. So it's how much are we moving the line through the axis. And theta 1 there is m, which is the gradient, so that's going to be the rate of change. How steep is the line that we're going to draw through the data?
So right now those symbols, those thetas, simply represent the variables that we see up there in our very familiar slope and y-intercept formula. Okay? All right.
So if we were just going to take a stab at this ourselves, we might just draw a line and go, okay, I think this is right. So let's guess that the gradient m, or our theta 1, is 0.1 and the y-intercept is 0.7. So our equation of the line is going to be y equals, and you can read that. But now we need a way, now we've guessed, of working out how right or wrong that is. We need like a numerical measure. So if we just look, we can tell from one example that the prediction's way off. So we've predicted that it's, sorry, this is pounds, that this is 1,200, sorry, I can't read that number there. But the actual price is way off. So for that one example, our guess doesn't fit at all. And now what we can do is we can measure for all of the examples how different is the prediction, the blue line, from the actual price that we can see. And then we've got this column here, absolute error, and that just means what's the distance in a one positive number. So just to remind you that this is our hypothesis, so instead of y equals mx plus c, we've got theta 0 plus theta 1 x. So now the way that we actually quantify that error between the guess and the prices is called the cost function, or the squared error function. And what we do is for every single data point, we go through and we compare what the hypothesis, the hx, has predicted with the actual answer that we have from the data, which is y. And we square it. And the reason we square it is because that exaggerates the problems that are really the really big discrepancies. So when we had a data point that was really far away from our hypothesis, that adds a lot more to the error than when we've got a tiny distance. And then we sum them all up and we kind of take an average. So just ignore the fact that it's 1 over 2m now, because that comes into differentiation later and you don't need to worry about that. But we're going to take an average. So we can see here we've got the squared error for all of the differences. And then what we do is we add up all of the squared errors, which is that number there. And then we're going to divide it by the number of examples, which is 10 times 2. And we get a horrible cost function result. So we've got a massive error. We've got this 4,418 figure. So the guess is probably quite wrong.
By the way, if you have any questions as we go along, please ask them. I should also say that although we're going into a lot of detail on math, it's not necessary to understand all the math to do machine learning because there are high-level libraries. But the title of this talk is Machine Learning Exposed. So what we're doing is we're taking the Band-Aid off quickly and we're exposing everything underneath the covers under machine learning. So when you're using those libraries, you know exactly what's going on underneath, right? So, but any questions before we go on?
Why is it 2 times 10, not just
Well, okay, let's repeat the question. Why is it 2 times 10 and not just 10?
So when we come to differentiate the cost function later, which I'll explain why we do that in a bit, if you've got any number like x squared, the differential is 2x. So we take that 2 and we moved it down and we times the whole thing by 2. So it's just to cancel that out when we come. So it's kind of, it's not precise maths, it's just kind of a bit of a cheat to make the differentiation easier. Okay, so now we've got our guess and we've got our way of quantifying how correct or incorrect the guess is. We can look at what the effect is of changing the theta value. So just to simplify this a bit, we're going to ignore that and we're just going to change this value here. So we're only looking at changing one value at a time. And we're going to see how that affects the cost. So if we plot the cost function here, so remember with our example earlier, we had this huge number, 4,418. You can see that as we change theta from one value to another, we've got points where the cost is really high, so it's an obviously wrong answer. And we've got this point at the bottom here where it looks like we've got a good value of theta because the cost is the lowest point. So when we run the algorithm later, that's what we're looking for. Can we work out the point at which it's at the lowest?
Okay, so what's the line on the bottom? What's the x-axis?
So this here is theta. So we're going to plot.
And the theta is the slope.
Yes,
Okay.
in this example, we're just
Okay.
looking at the slope of the line, so looking at the m of y equals mx plus c.
Okay, so we've got all these points on the graph, and we're trying different slopes to try to minimize our cost function. We're trying to get it as error-free as we can, as close to fitting the points on the graph. And so as we're changing the slope, making it, increasing it, which is represented by going over to the right, then we can see, based upon this graph, what it's doing to the overall cost, the error that we described. And so then as we do that, I'll let Katharine take it from there. Just wanted to make sure that we're all tracking.
So this is where the differentiation of the cost function comes in, because you saw from the graph we had this bow-shaped function. And what we can tell is there's a gradient to this bow shape. So please could you go back one slide, sorry.
Yes, I'm sorry.
So here, as theta's moving from 0.1 there, sorry these numbers are quite fuzzy, to 0.16, the cost function is decreasing. So we don't necessarily, when we're trying to work out this linear relationship, we don't necessarily want to run it through hundreds of different theta values. We want a way of saying, if I just give you one value, can you work out whether you need to go forwards or back? Do you need to increase or decrease theta? So gradient descent says, okay, the cost here is decreasing. So if we drew a line across that bow shape, the line is going down, so we know that we need to increase theta to get a lower cost. So that's what gradient descent does. So it goes, is the cost function increasing? Okay, so we're going to minimize theta because we don't want the cost to keep growing and growing, so we're going to get further and further away from the right answer. And if it's decreasing, then maybe we want to increase theta. So this is here the gradients in blue of the cost function. And at the bottom you can see it's 0. The gradient's 0. We've got to the bottom of the cost function, the optimal value of theta.
So if we had a tangent line at the bottom of that, it would be horizontal, which means that the cost is 0.
Yeah, it means we've reached the best value of theta.
So the cost isn't 0, but we've got the best cost at that point. So we've got the optimum value of our slope.
That's right.
Gotcha. I'm just making sure I'm catching up here. See, okay.
So in a generalized way, and I'm going to skip over this a bit so we can cover everything, what we would do is every time we change theta by a little bit, by this gradient, and you might notice another symbol there, and I'm sorry, it's alpha, and that is going to represent the learning rate, because if we have a big learning rate, we're going to take a big step, we're going to decrease theta by a lot. And if we have a small alpha, we're going to decrease it by a little bit. So it's a way for you to control how big those steps you take are. So if anyone is interested, you can refer back to the recording of the talk and have a look at the equations here. Please could you go back one? Sorry. Just for the benefit of the gentleman in red, this is where we've differentiated the cost function and we've lost our 2. So this is just a quick example of how changing alpha works. So you can see in this top example here, if we have a tiny alpha, we take lots of little steps to decrease the cost function. And then as it gets bigger, it might get too big, we can't converge to a good answer. Linear regression might not be the right answer, in which case you can create polynomials. Maybe the data isn't a straight line, it's a curve. And then you might want to look at increasing the complexity by squaring your data, or cubing, or whatever. When you've got more than one variable, gradient descent becomes really difficult. So remember before we just looked at the gradient, we just looked at the m. And if you look at different variables, then you end up with lots of dimensions. So if you have 2 theta values, you're going to have a 3-dimensional cost function graph because you've got one value versus another value versus the cost. If you've got 4, you've got 4 dimensions, and I'm afraid I can't illustrate that. And it goes up and up and up, and it increases in complexity.
So, for example, in the housing price, we had square feet, and then that ended up because there's slope and there is y-intercept. There's 2 thetas there.
Yeah.
We would have 2 dimensions, which is here. But then if we also had number of bathrooms, then that's another 2 dimensions. So now we have to represent the gradient here on 4 dimensions, and so it gets more complex. But that's the multivariable thing that you're talking about, correct? Yeah. Good.
Of course, linear regression isn't the answer to every problem. You might have data where it's just not obvious what the right thing to do is. And I'll leave that there.
Okay. Okay, so one of the classic data sets for learning and teaching machine learning is the iris data set. So it's a data set that has 150 records in it, and it contains the measurements of different iris plants, different species. And so there are 3 species, the iris setosa, the versicolor, and the virginica here. And then we have the sepal length and width, petal length and width. And then the training data set then lists those out with the correct answers. So that's a supervised learning problem. And so we need to be able to find, the machine learning algorithm needs to be able to find the separation between those different features, actually between the different species of iris, and needs to be able to find those boundaries. Those are called decision boundaries. So what you see in the graph here are the sepal length with the sepal width. That's one dimension, and we see those plotted in that dimension. And then sepal width to petal length to petal width, and then we can also see petal width to sepal length. So with 4 dimensions, there are 4 boundaries that we have to distinguish. And so there's one way of visualizing it. Another way of visualizing it is with tools that will visualize higher dimensional data and bring it down into 3 dimensions. So there's a product from Google. It's an open source product called TensorFlow, and they have a visualization API or UI, called TensorBoard that allows you to visualize higher dimensional data. And so I'll just pull up the iris data set. There it is. Okay, so here's the iris data set. There's the iris setosa, versicolor, and virginica. So in this 3-dimensional model, then we're representing the 4 dimensions that we need to be able to distinguish between, because there are 4 features. So that's a visualization technique that you'll see. So now we'll jump into this idea of artificial neural networks. So very loosely speaking, artificial neural networks are based upon our brain networks. So our brain networks have inputs. They're also called dendrites. They have outputs called axons. And we also have neurons. And we have, what's the fourth thing? What do we have? Synapses, yeah, that connect neurons. So we can model those in a computer artificial neural network. So to try to model that then, our inputs are in a layer, and an input layer has all these features like the dimensions of the petals for the iris data set or whatever, or number of bathrooms, square feet. And then we have hidden layers, and those are the neurons inside the brain. And then we have synapses that connect all the neurons. And then we have an output layer, which then we make a prediction. For example, is that, what is the species of the iris? Or what is the cost going to be of the house? So when I was first learning this stuff, I wanted to build a visualization tool so that I could understand the neural networks and as they're training, how the what's called the weights are being assigned into the neurons and the synapses as it's being trained. And so I put it on GitHub's. It's a Apache 2 license, so you can use it anytime. And it's here. So it's you run a server, and it's written in Spring and Java and other technologies, and then you run the browser against it. And so I can click on iris flower, for example, and I can see those inputs, and I can also see the neurons and the output layer. And I can see the weights. I'll go ahead and click it again. You can see as it's being trained, as it's being exposed to the data set, those numbers change. And so I can make, for example, a prediction here. I can say, okay, the sepal length, maybe I pick one in the wild, and maybe the sepal length is 5 centimeters. The sepal width is 3 centimeters. The petal length is 1 centimeter, and the petal width is 2 centimeters. And if I say predict, then it does this feed forward pass through the network using the weights that were in there when it was trained, and predicts with 0.99 confidence that that particular one is a setosa. Yes, question. Okay, so the question is, when you train the network, do you always does it always result in the same weights? And the cheers. How do you say cheers if I'm in Germany? How do I say cheers? Prost. Okay, so anyway, yeah, if you use the exact same data set and the exact same hyperparameters, configuration for the network, it's it'll all be the same. But typically, in the training cycle, you want to train it and then you want to optimize it, and so it never ends up being the same because you're always tweaking things. Good question. So this particular here's the architecture for the application that I just showed you. We're using this deep learning for J library, and then I'm using with Spring, I'm implementing REST services and neural net, WebSockets using an HTML5 client that I've written in Angular 2. I'm using the DL4J library. It's found at deeplearningforj.org. It's open source and free. And then start.spring.io is the best way to start doing the Spring project. And so now we are going to cover unsupervised learning and ask Katharine then to come back on stage. Oh, one question.
If I supply bits that are not matching this iris, I will break the neural network, right?
Okay, so the question is, if we supplied, when we did the prediction, like if I supplied values that weren't in range, would I break it? it wouldn't break it, but it might come up with an inaccurate prediction because it's kind of out of range of what the network was trained, and so but no, you would not break the network. You can't break a network.
Yeah,
So.
I meant like an exception, but as a behavior, because if I'm keep supplying the wrong values, I eventually will relearn the network.
Okay, so the assertion then is if I supply the wrong values as I'm asking it to predict things, it's actually training the network bad behavior. And so there are two independent activities. One is where you train the network with data, giving it features and labels, and then and that can be a slow process sometimes. And then you are another separate activity is then I make use of those values and I leverage it with predictions, and I say, okay, now tell me. And so you can make it so, and as a matter of fact, by default, when I do predictions, it's not actually training the network. So, okay, so Katharine, take it away.
Okay, so we've looked at supervised learning where we have the labels. So we've said these are the right answers. If I tell you the data that I've got in and the correct answers, can you work out what the pattern is between them? And unsupervised learning is when maybe actually you just don't know what the right answers are. So an example might be on Facebook, you have friends and connections with people, and they want to work out what are the clusters of people, what are the friendship groups. But there isn't an option on Facebook to say, this person's in my friendship group. So they need a way of working that out. So imagine we have some data here, and we don't know what the relationship is. We can see just by looking at it that there seem to be two groups. Okay, so just by looking visually, we can see that actually we might split this data into two different segments. And the problem is, oh, sorry, please go back. The problem is, if we have this data, we can't always just easily visualize it. So we want a way to do this programmatically. So one way is the k-means algorithm. And k is just, it is actually a confusing name for an algorithm, to be honest. But we're going to pick like two clusters. So k might be 2. If we would pick 3 clusters or 4 clusters, k would be 3 or 4. So it's a way of saying the number of clusters I want means algorithm, but k just to confuse you.
K for confuse.
Yeah, k
Okay.
for confused. So what we can do in the k-means algorithm is we're going to say here that k is 2. We want 2 clusters. And we're going to randomly initialize 2 points, and they're called the centroids. And you can just think of centroids as meaning the cluster center. So we're going to say, okay, I want you to find these 2 clusters. Here are 2 data points. Let's just start with 2 random data points for our 2 clusters. And we're going to call them, just to confuse you again, mu1, which is that Greek, we love Greek letters, another Greek letter there, and mu2. And that's just a way of saying that's one centroid, and that's another centroid. So I'm just going to call them centroid 1 and centroid 2, but we'll use that symbol. And now what we do when we've randomly initialized those is we go through every one of the data points, so every one of the red dots, and we say, how close are you to each one of those centroids? So how close is the red dot there labeled with X to our first centroid? And then we look at how close it is to the second centroid, and we look at the Euclidean distance, which is just what's the distance between these 2 points. And we can see here, even though visually you can see straight away that it's closest to the first one, numerically it's closest to the first one as well. So once we've worked out for every single data point which of those centroids it's closest to, we can then group them. So we say you, data point, belong to the first centroid. So you're going to be in group 1.
So what's Euclidean distance?
It's like a way of measuring the absolute distance between 2 points.
I know about the Pythagorean theorem. Does it have anything to do with that?
Yes, it does.
Oh, like what?
So, sorry, I can't laugh with this microphone. So it's like if you're sat at your desk and you want to go to the bathroom, and maybe to get to the bathroom you have to walk round a wall and then go like this, turn a corner. And so you know how far you've walked in steps, but you want to know what the distance is between where you are and where the bathroom is. So just like in a triangle where you can work out that third side.
The hypotenuse?
Yes, exactly. You're going, okay, so I'm going to work out using what I know about how far I step, using the Pythagorean theory to work out what the distance is between you and the bathroom. So that's what we're doing.
Okay, so in 2 dimensions, I can use, you know, a squared plus b squared equals c squared, right?
Yeah.
And if I had 3 dimensions, I could a squared plus b squared plus c squared equals d squared, and on and on and on. But I'm always measuring the hypotenuse in however many dimensions between one coordinate and the other coordinate, and that's Euclidean distance, correct?
Yep.
Great.
So now we've measured the distance, we can see that for these data points here in blue, they're closest to the second centroid. The data points in red are closest to the first centroid. So now what we've done is we've assigned them. So we've randomly initialized the centroids, and we've assigned the data points to the centroids. The next step is to, so this is just an illustration that you might keep track of where they are with a vector C. The next step is to look at those centroids and say, okay, for my group, my second group, what's the middle of that group? What's the center of that group? So what we do here, so just using the red dots because there are less of them as an example, the top group, mu1, we're going to add up all of the vectors, all of the dimensions. So for example, we've got 6 along, 7 up, we've got 8 along, 7 up, and so on, and we average them. So we take the middle distance of those points. And then we're going to move the centroids. So we're going to move them into the middle of those locations. So now what we've done is we've assigned all of the data points to a centroid, and then we've moved the centroids to the middle of that point. Then we can reassign the data points again, and the k-means algorithm repeats this and repeats this and repeats this until you converge into your clusters. So you can see now that we've roughly converged into those 2 groups that we first identified. So just to go over it again, so we've picked our k clusters, 2. We randomly initialized the points. For each example, we worked out what centroid it was closest to, so that's the cluster assignment step. And then after that, we, for every centroid, work out what the middle of those data points are, and we move it, and that's called, imaginatively called, the move centroid step. There's a way of measuring the cost again, because we want to know how well it performed. We need a numerical way of saying this is a good cluster or this is a bad cluster. And the way we do that is for every data point now, we say, how close are you to the centroid that we think you belong to? And then we work out what the average is, so we can find out how well it's doing. And that is it.
Nice, nice.
Unless there are any questions.
How do you actually decide on what number of fields you use?
So
the question was?
How do you decide what number of k to use? It's a very good question. One way of doing it is to start with a number like 10, for example. And in the cluster assignment steps, when you're saying which data points are closest to which centroids, if you have a centroid that doesn't have any data assigned to it, you axe it. So that's one way of doing it. That's the tricky bit of the whole thing, is choosing the number of clusters. Another way to do it is look at the cost function. If you've got a really high cost function, maybe you don't have enough centroids. Maybe your data points are really far away because you've only chosen 2 points, but actually you've got 5 different groups. So that's the tricky bit.
Okay, so I'd like to move on now to getting into some other types of neural networks. We've got artificial neural networks, which we showed you, which were, we're modeling the brain, and we've got neurons and synapses and things like this. So there are other configurations of artificial neural networks that are used for special things. For example, in image recognition, as studies have shown that animals, including humans, when we look at things, we're actually picking out higher level features out of something rather than seeing the whole image at one time. And so we model this with machine learning algorithms in what's called a convolutional neural network. And so there's this page on the the Stanford website that then has a convolutional neural network actually running in a browser, the prediction side. And there's a link to this in the presentation. So it's just showing pictures, and then it's showing in each layer of the network, in this convolutional network, what it sees. And so the next slide then kind of shows a little bit deeper view of what a convolutional network is. So over here on the right is our familiar fully connected layers where we have neurons and synapses between them. But then up front we have one or more convolutional layers where we've got the image coming in, and we've got this convolution thing happening, and then we've got this pooling thing happening which downsizes the image. And that way, when we get to here, we're presenting higher level features to the fully connected parts of the network. And rather than being maybe thousands of values in these pixels, we're boiling it down to a smaller vector that we can have a fully connected layer on. So to graphically depict this, there's a really nice visualization that this person named Adam Harley created, and here's the link to it. But I can visualize a convolutional network that recognizes handwritten digits. So this data set of handwritten digits, it was actually trained with this data set called MNIST for the post office, so that when people were writing zip codes that you could recognize them. So I could go ahead and draw a number here. Maybe I'll draw a number 8. And so we see, as soon as I do that this is the input. And then we have convolutional layers. And so you can see the lines going from pixels in each of these vectors in the convolutional layer, showing what it is examining and filtering for that particular thing. And then here's a pooling layer where it kind of downsamples the image. And then we go again. Here we do filters in this convolutional layer. We downsample it, and then we end up with a layer of neurons that's fully connected to each of the values, the neurons in this layer, this last pooling layer. And then here we have another layer that has it's fully connected, with our normal neurons. And then, as with our artificial networks that we've seen before, I'll go ahead and drill into this. Then we have our prediction that says 8. So this last layer here is sometimes called the FC7, the fully connected 7 layer. It's an arbitrary number, but it conveniently stores this nice vector that boils down these high-level features for whatever the image was into this code that you can then use for nice things later. And so then visualizing high-dimensional space, this MNIST data set has lots of images of 28 by 28 grayscale pixels. And so to visualize that, we can use this TensorFlow embedding projector again. And it's going to use this, what's called a PCA algorithm, principal component analysis algorithm, which takes high-dimensional vectors. So these high dimension, the actual images are 784 pixels of 0 to 2255 grayscales, and so that's a vector with 784 dimensions. So it takes and uses the PCA algorithm to then be able to see those in 3D space. And so we see how the 2s are over here, and we can see then, we can begin to see how we can make those decision boundaries and tell which ones are which. Yeah. And so that's an easy way to be able to visualize high dimensional data. Okay, so then another thing, it's kind of a newer technique. If you're at a cocktail party sometime and you're talking to some machine learning people, and all you have to do is talk about, hey, have you learned about generative adversarial networks? And because it's the coolest thing. And what it is this ability for the neural network to hallucinate, to kind of dream up images that don't exist. And so these are all images of faces that aren't real images. They're ones that the neural network has dreamed up. And so the link, by the way, down here to the paper or to the website is pretty fascinating. But what it uses is this concept of a counterfeiter and a detective. So what happens is you train a neural network, a convolutional neural network, with a bunch of faces, and then you have this discriminator, which is the detective, and you have this generator, which is the counterfeiter, and they're playing this game where the generator draws a picture of a face, and the discriminator says, oh, that's fake, or that's real, and then shares with the generator, why he thinks it's fake or real. And so the generator gets smarter in generating the images, but the discriminator gets smarter in being able to discriminate between them, discriminate whether it's fake or real. And so then what you end up is with these images that end up looking more and more real. And so then when you're doing that, then you can take that, remember that FC7 layer, that kind of last layer in the network before the prediction. In this particular application, they've got 100 element or dimension vectors with these grayscale numbers. And it turns out you can do math on them. So you can take the vector that represents the man with the glasses and then subtract one that with a man, a picture that was generated with a man without glasses, and then add a woman without glasses, and that equals a woman with glasses, right? And so it just generates then a woman with glasses, even though that one didn't exist either. So you can do this kind of cool vector math. And so the last thing I'd like to talk about is recurrent neural networks. And so the networks that I've talked about so far deal with static information. So give a house price in square feet or an image. In this case, we want to be able to do things with time series. We want to be able to have this ordered set of events that happens and then maybe predict the next thing. Or in the case that so in this case of the cats, if the computer saw that, if we ran that through a convolutional neural network, it would say, okay, there's a couple cats and a box, but it can't really say what's going to happen next. So I don't know. What do you think happens next? Somebody tell me. The box closes, right? So, but equally as probable, I suppose, is maybe the white cat down there is stronger than the black cat, and the box opens. And so this was fun looking at GIFs all afternoon, the other afternoon. But you are right. Actually, the box is closing, but it could have been opening, right? Right? So pretty much like every afternoon, I watch cat GIFs. But so you could use that kind of thing with music composition. And then in the slides, I don't have time to do it now, but in the slides, there's a really nice site that was made by Google Brain and an experiment off of that where you can actually jam with a neural network. It's kind of cool. And then I think we close with a video then of what a self-driving car sees. So this is a video that was produced by Tesla, and they put it out just to show what the driver sees, but the driver isn't holding the wheel or controlling this in any way. But then also over here, what the car sees with sensors and via machine learning. So it's with convolutional neural nets, it's picking out things like stoplights, traffic signs, people. It's a good thing. Should pick out people for sure. And then can see what's on the right of it, front of it, in the rear of it, and then using that to make decisions on driving. So thank you for your attentiveness, and we do have a few minutes for questions after this. Who's got the first question?
Why some boxes are blue and some are green?
I don't know. Sorry. Other questions? Okay, well, thank you for your attentiveness. By the way, we have a follow-on session that we're going to be diving into deep neural networks and reinforcement learning after lunch. So thank you very much for your attention.
Thank you.